So this is actually a source of great pride for me to introduce Rob Neely as the keynote speaker for today. It's not often that you get to introduce one of your former students as a keynote speaker. So those of you who don't know, Rob Neely is a PPL graduate, from University of Illinois, and did a master's here in 1994, not just Illinois, but in this group. In fact, it was only recently that I dusted off his master's thesis and asked one or two students to look at it, because it was on the process groups, and you know, those are the concepts that we had to keep shelve them because they didn't become important. Machines were not large enough, and now the machines are large, and we're bringing back new scalable algorithms for forming process groups. So there is a talk tomorrow, Rob, on that topic as well. So Rob got his master's degree here and then went to Livermore, and that's where he has been for most of his time. He has been working on integrated codes, the ASC integrated codes, and he was a lead computer scientist on the AL3D project. So he spent 1 year, or is it 1 year, at in Washington D.C. for working on the competitiveness council, the council on competitiveness. They are trying to figure out how to what's the status of HP with the broad industry and how to promote that. And he's now back to Livermore. He's leading the advanced architecture software development project at Livermore, and of course. He's one of the key people who is figuring out what DOE is going to do at Exascale. So, Rob?
All right. So yeah, it's great to be back. I was in this group. I was not in this building. This is a beautiful building. This is, you guys are lucky. I don't even know if the old DCL is still there or if it's now used for something else. But yeah, so like Sanjay said, I graduated from here in 1994. The landscape was a little bit different back then. MPI was, I think, still in the forum stages. The standard had not been released yet. PVM, if anybody's ever heard of that, was probably the dominant message passing language at the time. Yeah, I got one semi-gray beard nodding here along with me. But yeah, that process groups work, I think, was inspired by some of the dynamic group creation in PVM as much as anything. But it's something that I think is missing. Well, it's not missing, but it's certainly wasn't as easy to do in MPI as it was in PVM. So let's see. I'm going to give a talk today. This is an overview of what we're doing at Livermore. This is really a proxy for the kind of things that's going on at all the DOE labs and NSF centers and elsewhere. But we've got some unique concerns with these multi-physics applications, which I'll describe what those are toward the beginning here. So an overview, I'll already said a little bit on my background. Some of the ASC perspective. ASC is the Advanced Simulation Computing Initiative, which has been really driving high performance computing at the DOE, at least on the defense laboratory side, for a good 15 years now. Multi-physics applications. I'll talk a little bit about CoDesign and proxy applications. This is how we plan on working with folks like you to help us get through these challenges. I'm going to do a quick survey. Depending on how much time I have, it may be pretty quick, on a number of projects going on at Livermore. If something catches your eye, contact me afterwards, and I can give you some more information. And then finally, I'll talk about a programming model survey we did about 6 months ago or so that was released, of which Charm was and AMPI were one of the programming models we looked at there. So it was interesting to hear Sanjay's introduction speech. This idea of over-decomposition, I think, is really powerful. And when I first went to Livermore, I had the lucky task of being handed a large project and said, okay, this runs great on our crays. Remember those vectorization, big cray machines? The world is changing. It's all about MPP, massive parallelization, which massive at the time was about 128 or maybe 512, something like that. But the idea of distributed memory parallelism was everybody saw that as the future, and so I had the opportunity to take an existing code and pretty much rewrite it from almost scratch in C at the time and MPI. And this idea of over-decomposition was something I actually carried forward, not in Charm++, but into the design of the MPI language. And that was when we did the domain decomposition there, instead of the normal idea of, okay, I want to run on 128 processors, I'll decompose into 128 partitions. We said, well, let's relax that a little bit, and let's say, you know, decompose into 1,000 partitions, and then you can run those on any number of processors, 1,000 or less. And it wasn't so much for the idea of load balancing and transfer, although that was always in the back of our mind that this would be a great way to migrate processes, because it would allow you to move large chunks of work without having to redo unstructured mesh decompositions and that sort of thing. But interestingly, at the time, it turned out that it was a great way to get cache performance, because, you know, typically you'd have these finite element domains of 20,000 elements or so, which would spill out of, you know, cache or whatever, you know, usually L2 cache. Whereas if you could take that 20,000 elements and chunk it into maybe 2 or 4 smaller work sets and then work on those sequentially, individually, you could actually get some performance. Turns out, as we unvectorized the algorithms in the code and made them a little more cache friendly, that that benefit went away. But the benefit that you could, you know, oh, I've got this problem that runs on 1,000 processors, but geez, you know, during the day I'm only allowed an allocation of 256. You can still pick up that problem and run maybe 4 times slower. You know, that was a big benefit. So the idea of over decomposition, I'll just point out, was you know, used as an inspiration for something that's still core to the large codes I'm talking about here. So, quick background on Exascale. Most of you have probably heard some version of this if you're paying attention to what's going on in the community. But as you know, Exascale is a hot topic these days, and since 2008, 2009, you know, there's been a lot of work going on in both the Office of Science and NNSA, which are the two halves of the Department of Energy. You know, this is the technical issues along the right there are a lot of the ones that Sanjay talked about, and these are the things that we're having to address head on. And this is a huge problem. I don't think I have to say too much more about that. It's been a long slog. I think in 2008 or 9, when we first held a number of the workshops that you see over here on the right, the Oscar office held these scientific grand challenges workshops to try to understand the drivers for exascale computing. You know, I think we all thought we'd be well on our way toward CoDesign and developing an exascale machine by now. You know, we're still not there. This has been a tough environment to get a large multi-billion-dollar program going. This is just a brief history of some of the highlights, at least from our perspective. Some of them political, more than technical, but you know, it's probably a little bit of out of date because some things are happening here in 12, such as a program called Fast Forward, which is a way to get some money early to the vendors. The XStack proposals have, I think the second round of those now has been, didn't they do one in 2010 as well, I think? So there are some things going on. It's just, it's not happening at the pace I think we'd initially hoped. And of course, you know, we're not alone in this. Pretty much everybody is putting their stake in the ground that has a computing program in their country. You know, in particular, China, I think, is looking very aggressive. But obviously, Japan, Russia, France, India, and the EU as well. So I think the advantage we have here is, you know, if I'm pessimistic and I say we may not be able to build the first exascale piece of hardware, I think we've still clearly got the expertise in the software side, not just the applications, but on things like programming models and understanding how to use ideas like Charm++ and other new and emerging programming models to great effect on these machines. And that's where it really counts from my perspective, right? You can build a machine for the sake of building a machine, but we need to have the applications running on it, you know, to get the economic benefit out of it and the programmatic benefit out of it. This slide, there's a lot of data in this slide that you can't see. This is one of those management slides that we were asked to pull together for headquarters. So This is the kind of exercise I sometimes get pulled into. Bert Still at Livermore really did the heavy lifting on this, but basically we got asked the question as Exascale was looking more and more hard to get off the ground, well, what if we do nothing? What if we just let the marketplace drive this? When will we get to Exascale, and how will our codes work? And so I'll just try to point out the highlights here, but this top dotted line is sort of the target for Exascale machines. I think we wanted to have a 200 petaflop machine in 15 and Exascale in 2020. Was 2018 at one point. Now people talk about 2022. Whatever it is, there's a curve that gets us to Exascale in the next decade or so. These stars just represent what we call peg posts in the ASC predictive capability framework. So ASC has a stockpile stewardship mission, which is the nuclear weapons mission in this country. We don't want to be setting them off in Nevada anymore, so we do it through simulation. That's what's been driving the ASC program. And there's a number of these very, very compute-intensive problems that we need to knock down to get to predictive capability so that we really can believe the results of these codes without having to rely on past underground tests and that sort of thing. This purple line here sort of goes along with these peg points. This is our uncertainty quantification requirements. So if you're not familiar with the term uncertainty quantification, it's basically the idea that to run a single calculation and just believe the answer is unless you really believe you have a predictive code, that's not the way to go. You have to vary your parameter inputs systematically and understand what your error bounds are on the answer that you get out. And this necessarily means running hundreds, maybe thousands of simulations for each of these large calculations. And so if we just take the requirements that we have today, for relatively simple 2D, not even 3D calculations, and the number of systems that the DOE, the NNSA in particular, is asking us to study to make sure that these things continue to work, the petaflop requirements are going to quickly get up here into the tens and hundreds. So there's programmatic driver, I guess, is the point of those two lines. Now the what if we do nothing, and these ranges are meant to represent our uncertainty quantification, right? We went and spelunked through some of the data we got from the vendors in an RFI that the Exascale initiative held earlier this year, or I guess it was late last year. And they told us, they said, if we get Exascale initiative, we can accelerate the way we get to Exascale. If not, here's where we see the marketplace going. Things like data analytics and all that are where the big money is these days. And so it's not necessarily an HPC. So just taking away, let's just imagine we don't fund Exascale. We're going to end up with machines in 2020 somewhere out here, and I think this is in the 200 to 500 petaflop range. Now let's take into account the fact that we don't do anything to our codes. And Sanjay mentioned the memory per core is going down, and these codes that we've developed over 10, 15 years rely on, usually about 2 gigabytes per core and MPI everywhere. So I'll start by saying we know that ain't going to work going forward, but let's suppose that we're squeezed. We've got programmatic drivers here. We can't just sit down and rewrite these codes. So if we do nothing there, well, we're going to end up idling cores, right? The effective utilization of the peak of the machine is going to go down. That brings us down into this red bar range. So this is really do nothing, right? This is take our, our codes almost as is, which have some coarse-grained threading in them, and try to bring them forward onto future machines. And it doesn't take into account adding accelerators or anything like that. And then we looked at sort of the real gloom and doom factor here, which is the trend in memory bandwidth on the node, the B to F ratio, bandwidth to flops. And even if we could use all those cores, we're going to be more and more increasingly starved to get the data from main memory into those cores. So the idea that you can have a Ferrari, but if you're trying to drive it on the Washington Beltway or wherever in traffic, what good is it? And that quickly brings us down into this pretty pathetic range. The takeaway from this is, oh my gosh, we could be delivering machines in 2020 that are nominally 500 times faster or 100 times faster or whatever, but the performance on our codes couldn't be not much better than today. We've got to do something both on the hardware and the software side is the point here. At the labs, we're facing a big challenge on how to move these applications to exascale machines. You know, we liken it to steering a ship. You know, see the iceberg coming, you turn the wheel, and maybe a few years later, if you're lucky, you dodge it. But you know, the kind of software we're talking about here are you know, really at the leading edge of complexity. They've got, you know, when I say multi-physics, it isn't just 2 or 3 packages. It can be up to 10 different packages working in concert. You know, lots of third-party libraries, multi-million lines of code, multiple language, and the interoperability issues that come there. These packages can run on different meshes, different time steps, different temporal meshes and time steps. Variety of parallelism approaches. We've got code steering. Our users want to be able to go in there and fiddle with the calculation while it's running, for example. So, you know, long story short, these are not the kind of applications that you just say, oh, problem ahead, let's just you know, settle down for a year and rewrite things. This is a big issue for us, and part of what my role is to help coordinate how are we going to handle this. And it's not an easy task, but luckily, you know, we're not alone. There's a whole community that sees this coming. And oh, by the way, you know, these codes that we're using are, you know, used as part of a multi-billion-dollar mission. We can't just, you know, stop what we're doing and say, sorry, computers got hard. We're going to have to rewrite. You know, the powers that be, the politicians who fund these programs, still want us to answer the mail on these things. So, you know, rewriting in flight. So this is just an example of a multi-physics calculation. Out at Livermore, there's a huge facility called the National Ignition Facility, which is attempting to be the first place to have controlled fusion in the laboratory. And they're doing it not the cold fusion stir-a-cup way that's magical. This is brute force, right? It's 128 massive laser beams, you know, about 1 foot in diameter, that bounce all around a stadium-sized room and converge simultaneously on a little sphere. Actually, it looks like this, a hohlraum. It's about the size of your pinky fingernail, with a little tiny sphere of deuterium tritium gas in the middle. These little colorful rainbows are the various laser beams coming in, and they hit this canister which emits X-rays, and you want to have perfectly spherical implosion of this little pellet, more energy out than you get in. Pretty cool stuff. In fact, they're filming the next Star Trek movie there this week. We got that, that's public now, so I can say that. So it's such a futuristic looking place, they decided that it was worthy of a Star Trek set. So, but to solve this, you know, right now we've got primarily three codes that are tackling various aspects of the problem, things like plasma blow off and the laser plasma interaction, and then, you know, understanding the material effects in the capsule implosion. What we'd like to do is make these things, each of these individual applications, not only more predictive, increase time scales, you know, increase the resolution all around, but couple them together. Right now, these are done separately, and the idea of multi-physics is that if you can couple these packages together, you can typically get more accurate solutions. But each of these on themselves could take up an entire, you know, blue gene machine on their own. And then you've got things like modeling what's called in situ diagnostics, or the things that are trying to understand. This is an actual picture of a NIF implosion, obviously false colored, but you know, you want to get perfect sphericity to get fusion, and as you can see, it's uneven there. So yeah, that's a great question. I mean, the diagnostics on this machine are, you know, amazing. If go to YouTube sometime, not now, I'm talking, but go to YouTube sometime and look up a video called How NIF Works. It's about a 4-minute animation video that shows how this thing is designed. It doesn't talk about the diagnostics specifically, but and there's a web page that probably has a lot of that information. But short answer, I don't know. But back to multiphysics. So here's really the crux of why this is such a hard problem. If you look at single physics codes like NAMD or something, you know, like that, there's typically one or maybe a handful of communication patterns and characteristics that you have to address. Well, in a large multiphysics code, you know, I said you may have 10 plus different packages. We just picked out 4 representative ones here: hydrodynamics, 2 types of transport, and then diffusion. and then looked at some of the typical characteristics of these algorithms. You know, how much memory do they require per zone in this case, or finite element in your mesh? What's the memory access patterns, communication patterns? What kind of computational intensity do you get? That sort of thing. And I just highlighted in red here where the pain points are for us, and the point being that they're all over the map. We can't just say, let's solve one of these problems and our codes will run. You have to sort of beat all these moles down simultaneously. So the big question, you know, do we, you know, taking from the revolution, evolution terminology, do we evolve our existing codes there, or is it time to just step back and do a rewrite? And I'd say this is, you know, probably question number one that I'm having to address right now, or help address. Certainly we have to continue to evolve our existing code bases. And we've got a new Blue Gene machine that's probably going to be installed right about the time Blue Waters gets turned on. I think all our racks are delivered, so we may be a month or two ahead. But it's a 20 petaflop machine, Blue Gene machine. We're going to get a lot of experience on that, obviously. It's got 1.6 million cores. Each of those have symmetric multi-threading, or what Intel calls hyper-threading, so you can uncover up to 6 million degrees of parallelism on there. Just trying to get our codes running on that, that's a good proxy for the kinds of challenges we're going to have moving forward. You know, we're going to have to begin implementing things like fine-grained threading down at the loop level. We got to deal with resilience. We're going to have to look at heterogeneity and things like GPU directives as a stepping stone to get there. And, you know, the reason I mentioned we're doing this rewrite in flight, we've got a huge validated code base that that's going to require us to at least take these codes forward for the next 5 years at least. You know, on the other side, we could undertake a new from-scratch rewrite, and you know, to understand when do we need to do that. We're getting some experience with some of the new programming models. That's one of the reasons I'm out here, is to get an update on what's going on in Charm and see if we can engage you guys in helping us with this exploration. We're developing these things called proxy applications that will help us streamline some of these explorations. So these multi-physics codes are too big to just say, oh, let's do a Charm version of this. But if we can build some simplified versions, then that certainly, you know, makes it easier for us to collaborate with and wrap our own heads around it. You know, and the takeaway here is, you know, it's too early. If I was told, Rob, go start a new code today, use whatever language you want, you know, I don't know that it would look terribly different than what we're doing today, which is largely C++, MPI, OpenMP, and probably OpenACC, right? The MPI plus XYZ. Just because, you know, these more these newer programming models, which, you know, I'm thinking largely of like Chapel and XTEM, but I'll include Charm and Swarm in there. We don't have enough of an understanding yet on how appropriate they are. So this is where we're, you know, it's important for us to reach forward and understand what's going on in the community to know what to put our weight behind. So Sanjay mentioned I lead a project called the Advanced Architecture Software Development Project. Probably at one point it would have been called the Exascale Software Development Project, but I think, you know, this isn't just about Exascale anymore, right? It's even if Exascale doesn't happen, or it doesn't happen until 2025 or whatever, we got a lot of problems on our hands just looking at node architectures moving forward. So this is really designed to take the things I'm talking about and coordinate it. And this is a lot of you know, lab mumbo jumbo here, but the idea is that, you know, we're trying to make sure we're reaching out from the applications team and working with the rest of the community. And, you know, so the project is designed to provide some free energy for those application developers to get out and work with folks like you. If you've worked with people from Livermore, they're probably coming from the research division, Bronis's group or Martin, and I don't know if you guys know that Livermore crowd, but they're on the research side. They're doing a lot of the fundamental math and computer science research. I'm coming at this more from the application side. These guys writing the big multi-physics apps. This is just a chart I use for my management to show the kinds of things we're beginning to explore. I'm not going to go into detail on these, but we're looking at, you know, how can we extract more on node concurrency? What are some memory models and resilience models we can look at? Proxy app development, I'm going to talk about that quite a little bit more. We're increasing our collaborations and exploring some more programming models. So all this happens under the banner of CoDesign. How many of you have heard of CoDesign? Right, pretty much everybody. So it's become a new term in the lexicon of high performance computing in the last 3 or 4 years or so. And the idea here is, I guess I don't have to explain it, but I will. It's that this is such a hard problem. We can't just take the machines, that they would deliver without input from the software side and expect our software to run nicely. And likewise, not likewise. We do want to have some say over the trade-offs that are being made as exascale computers are designed as software programmers. And you go back to one of the original DARPA studies, they were talking about, oh, exascale, you'll never have, ECC or memory parity or whatever. It's too expensive. And it was just like, whoa, showstopper. Not an option. There's some fundamental level of capabilities on these machines that if we don't have, they're just not useful. And so CoDesign is the process of streamlining that. And the Office of Science has 3 CoDesign centers set up. Are you involved in any of those? So, and then NNSA, which is the defense side of DOE where I work. We're standing up either our own CoDesign centers or figuring out how to better collaborate with the Oscar centers. CoDesign's a tricky problem. You think of CoDesign, people talk about the use of proxy applications, which are these open released applications, and the vendors coming forward, and we have meetings and telecons and trade people back and forth, and we understand each other's problems and move forward. And that's sort of the idyllic view of CoDesign. The fact is, very quickly you get into non-disclosure agreements and well, are you working with Intel and IBM too? Well, it begins to, the lawyers get involved in all that. And likewise on the application side that I'm on, even our unclassified applications, which we have a lot of, are typically not ones that we can just give to a university. They're export controlled. You take it one notch beyond that, and that's where reality hits. You get into what these vendors call deep NDA, where you want to see our roadmap 5 years out before we're even doing tape out. We want you to sign something that says you're definitely not going to be talking to anybody else. And that's a problem for us, right? This is not what we thought of CoDesign going into it, but it's getting very sticky. So, and on the symmetric side, on the application side, we've got classified applications that are really what we want, to work in CoDesign. How do we, bridge this gap? So this is where a lot of the slog is going on in the CoDesign community right now, is trying to understand how to best tackle this problem here. So proxy applications, these are these simplified applications I talked about as a core strategy. The idea is that you take your full code, in our case it may be behind the fence or at least something we can't release, and you build a proxy app from that, looking at what the metrics are and understanding where are the hot spots or the problem spots. You apply some candidate transformations on that. You try to make it better. You make it faster. Doing your best to predict, looking forward where, what those architectures are going to look like. Then you pull that back and you apply those lessons to the full code and make sure that that you did actually improve it. And remember that, chart I showed with all the different red text in various spots. The issue we have is we may make, for example, some data structure transformations so that something will work better on GPUs in one package, but that may be exactly the opposite thing that we want to do for one of the other packages. So this is the iteration loop that we're in now, or just beginning to get in. And proxy apps, you'll hear people talk about, there is no standard taxonomy for them, but at the very bottom level you have kernels, which are what you think. They're just small little kernels to explore things like maybe accelerators or whatever. Skeleton applications, which are applications with all the numerics taken out, designed to look at things like message passing at scale. Mini apps or compact apps are these simpler ones, and then you have the full actual applications. But the idea of this chart is to show that there's a second axis here, which is we don't just want to do CoDesign to understand numerical performance. We want to understand design of networking. So you talked a little bit about you're beginning to look at that. how can we actually write brand new algorithms, not just take the algorithms and code we have and make them faster, but just completely rethink the way we do things. System software, I mentioned at the beginning, we have a lot of codes that do steering with Python or something like that. What are the operating system requirements you're going to need on an exascale system? If these compute level or these compute node kernels don't support what you're going to need to do that sort of interactivity, then we either have to redesign our codes around that or influence the vendors so that they do. And then likewise, we want to use these proxy apps to explore new programming models. And this is where I'll talk toward the end about, I think what we'd like to do is take some of these applications and begin to do some explorations and things like Charm++ with them. So proxy apps, it's important to know these are not just benchmark codes. So you hear about, every acquisition we have, we've got a set of benchmark codes, and they go out there, and you guys are free to download those and use them. These are really meant to be more of an iterative process. We want to work with the community through CoDesign to get these, get the lessons learned out there back into these proxy apps. So these are going to be living, breathing, moving, fluid applications, and we're just now getting that stood up. So one of the first proxy apps we developed was under what's called an LDRD, or this is internal lab research. This is a code this is the AL3D code that I worked on for years. It's you don't have to understand any of this other than it's got a lot of moving pieces to it. And the proxy app we developed, we basically took some subset of it. Most of the services that come with it, and this Vista is a sort of domain-specific language we built to support mesh structures. But we extracted the hydrodynamics, thermal, and advection packages as a proxy for, okay, now we've got a somewhat smaller code we can use to do some of these explorations on. And in addition to that, we're just now beginning to pull together a table of I'll say proposed proxy apps, because this is just literally a working list of, what do we have in-house that we can use, and let's write them all down. Let's begin to do a gap analysis of, does this set of applications cover all the areas we think? And this is something that's work in progress. And green, they exist. We could probably give them to you today. Yellow are in development, or I think these are actually done. They just haven't been released through some sort of open source license. We've got a number in development, and then some ideas. This isn't quite ready yet, but codesign.llnl.gov is where we'll keep an updated list of this and have some sort of download site. Hopefully by the end of this week, that site will be ready. Just last night at midnight, I filled out some paperwork to try to get that through the system. So we'll see if that happens. That's a good question. And like I said, there's no accepted perfect taxonomy for this, and I tend to lump them together. But in the past, people have talked about compact apps as being sort of one level simpler than the mini app, or maybe it's vice versa. I can't remember. But there was an idea that compact apps, or I guess it's mini apps, are one step closer to the actual final application, whereas the compact apps, might be full applications. They do something useful, but much, much simpler than you would have. So it's just a degree. And I'll be honest, I've already forgotten which direction that goes. So we have released 2 new proxy apps this year. One, LULESH, which is an unstructured Lagrange shock hydro. This is something we developed initially for the DARPA UHPC program, which I think Illinois is involved in, aren't they? Joseph, maybe? So they wanted a suite of benchmark codes, and so we came in and proposed this, and it's turned out to be a great application. I think there's 8 versions of it and counting now. So in fact, I think we've even talked about doing a Charm++ version this summer with one of the students. And Mulard is one that's being released soon. This is a somewhat more complicated multi-group radiation diffusion package. It's built on a library called MFEM, which is co-developed through, I think, University of Texas and Livermore. But this is a great example of how we would design a proxy app from scratch, because it's got some switches built into it to allow you to do some explorations in how you do, in this case, matrix construction. So in multi-group radiation diffusion, you've obviously got multiple groups. You can either assemble all those groups at once and do one solve, or do them one at a time, and there's pros and cons to both depending on the machine, depending on the characteristics of your network and all that. So this is an application designed to explore that. So LULESH is probably 2,000 lines order, and maybe the MPI version a little bit more than that. Mulard is probably the main application, if you don't count the library under it, is maybe 5,000 lines, and then the MFEM library, which is on Google Code, is probably another 25,000 lines or so. So we want them to be simple enough that somebody can wrap their heads around them quickly, but they can't be so simple that they're not representative. And this is actually an area that I think is going to be a big research focus for us this year, is how can we tell if these proxy apps are representative of our full applications? Right? What are the metrics we should apply? Can we just look at instruction mix using tools like HPC Toolkit or whatever, Open Speed Shop, and say, yep, that's good enough? Or, I think the answer is no. We've got to dive down a few levels more and understand, if we say these proxy apps, we work with the vendors and the community to say, you get these right, we think our main applications will work. That's a hard question to answer. So that's something that we're addressing more on the tools and metrics side. So we do have some existing platforms that's giving us some insight into this. We've got a 150,000 core Blue Gene P machine, which we've had for about 3 years. And this is our early delivery for the Sequoia machine I mentioned is coming, and we've got another 1 petaflop Linux cluster that's pretty new. I think the things we're finding is that the scalability issues are, not always in things like the linear solver. They're where, some application developer put some order P or number of processors array in their code to, maybe keep the extents of each domain, and, well, it's only 6 words per domain. Well, when you get to 10 million domains, right, it begins to add up, especially when your memory per core is diving down. We're really having to address the threading issue head on. Sequoia is, I'll say it's an IBM machine. It's not the Blue Waters design. It's a different design completely. But threading is really going to be a requirement for us to extract full performance on that, and that's the first machine we've had where that's been the case. I think we can do a lot with MPI everywhere, but the people who want to get the best performance on this are going to have to take one step further, and that's sort of the perfect spot we want to be, right, is not put a machine on the floor where we have to suddenly stop for a year and do aggressive changes, but something that's really forcing us along this evolutionary path that we know we have to be on anyway. And then I'll talk a little bit more about some resilience things we're doing later on. No, so I mentioned threading. So yeah, we're dusting off our OpenMP books, right? So a lot of us looked at OpenMP back in the probably early 2000s when clusters of SMPs first came around, and didn't have a whole lot of success with it. I think we're running into a lot of the issues that we're still running into, right, is the serial sections in your code and the amount of overhead for spawning threads. And it turned out that MPI everywhere actually worked better than trying to do coarse-grained threading. So we're rediscovering all these issues, and we're introducing a new fun thing here with Sequoia, the Blue Gene Q machine, called transactional memory. Are people familiar with that? So it's in a nutshell, the idea is that, say you've got a loop, and normally you'd have some potential race condition in there, and the normal way you would do that is put some atomic operation around it or critical section, and you're paying for that lock every time you go through that piece of code, just in case you had a collision. The idea with transactional memory is define that as a transaction. Don't put a lock on it every time, but the hardware will detect if there's a collision, and if there is, do automatic hardware rollback for you. So if you've got a piece of code where you might have some sort of race condition on a piece of memory, but it's going to just be every once in a while, to be defined what that means, but every 1,000th iteration or whatever. Try transactional memory. You pay a lot more for that rollback when it does happen, but you're not paying that overhead of locks every time. And Blue Gene Q is the first machine, I think the first machine to support hardware transactional memory. There's been software transactional memory in the past, but so this is very new. I don't think we have we have one guy who's really done some deep explorations with this outside of IBM, and so far it's looked pretty promising. So, talking about fine-grained threading, you drill down into our codes, you see a lot of this kind of thing. You've got, maybe a loop over zones and then over some region in there, and then you've got these guys stacked together. Right now these are all sitting on MPI tasks and probably not even threaded with OpenMP. One thing we're looking at is the threaded building block stuff and its pipeline construct. The idea here is that you can actually take these loops as each individual work chunks, and threads that are going to work on this data can actually begin work before this block of work is completed. So literally pipelining work. And it's a bit disruptive. The syntax isn't totally clean. It's not just adding a pragma at the beginning, but it's an interesting concept, and should help avoid what would normally be an implicit barrier at the end of that loop. Yes?
It's better to have the end roll back to the slide, because what's the potential for using automatic code generation so that you can just do fusion, which is over the own zone material stuff? Because that's the obvious solution that would give you vectorization, would limit all the barrier garbage. But I mean, I understand you've got 8 bazillion lines of code.
Yeah.
I mean, has somebody looked into the fact that if you, instead of writing physics libraries, you write physics code generators, and then you just put your for all junk at the top, and you get...
That's the kind of thing we're looking into. This is not the answer. This is one thing we're exploring. But yeah, you're right. Maybe loop fusion is the way to go. I think one of the examples, and I don't have it here in the slide deck, that the guy doing this, there was some kind of work going on in between here that it was actually better to break these up this way, and it may have had to do with the amount of temporary storage that was needed or something like that. Or it was probably spilling out of cache or something like that. That fusion was not the right way to go. So I can explore that and maybe come back and talk to you some more after I talk to the guy who's been doing this work.
So another thing, this is an interesting piece of work that a guy, Jeff Kiesler and Rich Horning, have been working on. So inside our codes, we have these concepts. We call them index sets. They're basically, if you've got something like a mesh here, and you just label each of these zones. Now, say you've got a material. This would be an ale mesh. So you've got some mixed materials, and you just need a list of, okay, which of these zones in this whole mesh contain this material? Okay, well, it's 1 through 20, 24, 32, 40. Normally in your code, you'd have to do some indirection here. And you'd loop over the length of this index set, and then through indirection extract the data out of this larger data structure. Kills vectorization, SIMD vectorization. You could do a gather scatter operation, but that requires more memory. So what these guys are looking at is there a way you could take advantage of the fact that, well, actually this index set does have a large contiguous block of memory, and if I take into account some sort of abstraction. In this case, they're exploring, iterators and functors and that sort of thing to make this somewhat clean in C++. But if you recall, you've got this index set that's got this range, and then which we're calling the structured range, and then some unstructured list. Normally, we'd have to treat the code entirely as this unstructured list and not be able to take advantage of that contiguous memory. But if you could understand where those structured and unstructured ranges are and build some sort of hybrid index set, actually have 2 versions of the loop, one with SIMD instructions, one without, you can take advantage of that. And this is very early work that's going on, but looks pretty promising because SIMD vectorization is becoming more and more important to be able to get performance out of things like the Intel Mic architecture or pretty much all architectures. That's one way they're extracting performance. And so, just to repeat, you'd have basically automatic code generation of 2 different versions of the loop. One that knew how to handle those structured pieces of the loop without the indirection. You could do vectorization, and then one that did have that. So we are doing some GPU explorations. We're not a lab that's necessarily known for its GPUs because we haven't deployed big machines like Titan, for example, with GPUs, or I guess does Blue Water's GPUs, at least on some of the nodes. So we that's not to say we're, we don't see the train coming there. So we did take that LULESH mini app and took one of the guys who's really an expert in CUDA. I mean, he writes, literally, video analysis software for satellite videos and that sort of thing, and has been doing, these kind of algorithms for a while. So we figured, let's get him. He's not a new guy learning CUDA. He knows how to do this stuff. And so he came in and did the best optimization he could. And, he was disappointed with a 10x speed up. I thought that was, not too shabby. But this is some early work going on. And again, we need to understand, how representative this is going to be of our larger applications. We're looking at things like, I guess MPMD style communication. I think you touched on this a little bit. Is are there ways you can run different packages on completely different sets of processors and coordinate a looser coupling between them? And so this diagram is just showing that package A and B may run on different pieces of the machine with some communication, and then join together and their data to run C on some other piece. Yes, you may be idling some parts of the machine at any one time, but in the grand scheme of things, if you can't fit all these packages on the same nodes together, this may be the way to go. So we've got some work looking at this too. In fact, that's being done through one of the CoDesign centers, the XMATX CoDesign Center. Flash memory, that's something that is starting to show up in machines, obviously, like the Flash or the Gordon machine at San Diego. The idea here is, can we use flash memory as a, well, for a number of things, but, for example, as a way to stage I/O. And if you look at the characteristics of disk, random access going all over the place is bad. Everybody trying to write to disk at once is bad, but it's really good at reading and writing. Whereas you look at something like flash, the inverse is true. Random access is good. Everybody can be beating on their piece of flash at the same time with little ill benefits, but writing to these to flash memory is there's issues with that. And I'm not going to spend too much time on this since I'm getting down to the end here, but this is some research that Maya Gokhale and Roger Pierce have been doing at Livermore. The idea is to just decorate your code with these items in red here, which basically say, these are my data structures I really care about. This is what I need. If a node goes down, I need to bring these guys back in and do a restart. And so just by decorating these, then in your code you detect when it's time to do some sort of checkpoint. With a single call, it will go out and store all these items in flash memory in this case, and then there's a converse restore. So the idea is using flash memory as one more level of the memory hierarchy for checkpointing in this case. And you can then, this is PERMA is the name of the project. ROSE is involved in some of this, but I think I've got a slide on ROSE coming up, actually next. Yeah, so if this is ROSE. So ROSE is our source-to-source compiler. Dan Quinlan is the project lead on that. And this isn't the same project, but this is one area that he's doing some interesting work with resilience. Looking at, well, say this is your original source code. This is what the user writes. Before the back-end compiler sees it, this is what we're translating it into. And the idea is basically, triple redundancy with a check. And whether or not this is something that's going to end up being useful to do, that's why it's research. But as resilience becomes more and more of an issue, this is the kind of thing we need to be looking at. Also with the ROSE tool, he's I think it's the Codex project, which is Berkeley and ROSE, and I think Sandia's SST simulator. But they're using ROSE to basically automate the building of these skeleton apps. And I quickly mentioned them before, but these are applications that, they're the full applications with all the communication and none of the useful numerics. So how can we, look at things like network scaling and all that without having to worry about the numerical? And so ROSE basically can come along and see if this came out. Yeah, it did. take a code like this, you know, and leave all the communication and reductions and everything intact, and automatically spit out something like this. It just saves the people developing these proxy apps from having to do that step. And again, this is something that's just been started. We got a number of other research areas going on at Livermore across the board. A lot of this is Bronis Desipinski's work. I'm not going to speak too much on it. So I mentioned this programming model survey. This is something a group of people at the lab did last summer and published, I think, in November. But it's a nice report that was really meant to help, you know, application developers like me get a quick view of the programming models landscape as it's looking for Exascale and characterizing each of these programming models. These are the ones that were looked at, the HPCS languages, Chapel and X10 in particular, some of the Intel tools, Silk Plus and the parallel building blocks, and then UPC, Charm, AMPI, and then the accelerator languages, OpenCL and CUDA. And you know, the report basically is a nice systematic approach to it that each chapter covers one programming model and, you know, has a nice, you know, table of where to find more information, and so it's really takes away a lot of the work of, you know, an end developer to get a quick view of what's going on, you know, not only in the, you know, most of the ecosystem. I don't think they covered everything, but they did do some, you know, interviews with the developers and that sort of thing. And then they, you know, it got subjective at some point where they said, you know, speaking to the developer community, what are some of the characteristics that would be pros or cons to a language? And, you know, the things that would be pros are some of the things that Sanjay talked about. Interoperability is a huge one right now. If we're going to evolve these applications, you know, we can't be expected to buy whole hog into these. These codes are going to live 20 plus years most likely. But do they have data structures that allow for things like adaptive meshing and sparse matrices? How nice is the language, right? That's a big thing, you know. If somebody comes in and their first reaction is blech, you know, then it's probably not going to be picked up. There's, you know, first impressions are everything, I guess. You know, is it based on something that maybe people already know that they can pick up? You know, I think the cons are maybe more telling. Does it require a really totally dramatic change in approach? Not that that's a showstopper, but you know, it may be the best thing to just completely throw out everything we've got and go to functional programming, for example. But you know, that may not be you know, realistic for some of these large code teams. Interoperability, I already mentioned that. Some of these maybe weren't heavily tested for scientific applications. Maybe they're really being targeted toward cloud computing and data analytics. And then functionality, you know, is it a one-trick pony? And so they came up with a set of recommendations. You know, in particular, as part of this, we've been talking to the Chapel team quite a bit and doing some of these explorations with the Intel. They did, as part of this, you know, recommend taking a closer look at Charm. And so, again, that's one reason I'm out here, is that's something we want to do. The report is available if you're interested at this website. You might be able to Google it, but I'm not sure if that'll hit or not. And these slides will be up on the thing by the end of the week, I guess. And this is just showing an example of CoDesign. In this case, it was Chapel. So the Chapel team, Brad Chamberlain, for those of you who know him, picked up this LULESH code at the beginning of last summer, had a summer student do a port in Chapel to it. Our programming model survey came out. We were starting to generate some excitement with Chapel internally. He came out to the lab, gave his, you know, 2-day tutorial. We, you know, said, hey, this is a really nice and elegant language. It ain't there yet, but we could see that, you know, at some time in the future, this could be, you know, an attractive programming environment. So we've begun to gain some familiarity with it. But one thing we noticed is that this isn't the picture, but that LULESH has a hard-coded mesh in it that actually looks like XYZ structured, but it's not. It's really an unstructured mesh underneath, and that was on purpose because we wanted to explore what the effects of indirection were, because a lot of our codes are unstructured. But they picked that up and looked at it and said, oh, structured mesh. I'll just rewrite this as a structured block structured code. And once we got that back, it was like, oh, nope, sorry. You cheated. You didn't read this one line in the 25 pages of documentation that said don't do that, right? And so we sent one of our guys back up there. I mean, they were, oops. And we sent one of our guys up there to, they said, well, come show us how to do this. And, basically in an afternoon, I think, total of 6 hours if you include a few coffee breaks they're in Seattle, so they probably went to the local coffee shop, right? But they were basically able to take what was fundamentally a block structured code and turn it into an unstructured code, with just a few lines of code change. And that would have been major in something like MPI. So the fact that Chapel had those abstractions that it could swing both between structured and unstructured that was impressive to us. And I think they're going to pull those changes back and now release their own version of LULESH that has a switch that says, okay, here's how you do it block structured, here's how you do it unstructured. So you can look all in one application side by side.
Documenting the process of that sort of change would be very useful.
Yes. Okay, so I'll wrap up here. We've got a message to our application developers that they can't stand still. There's a number of issues that we've talked about in this talk and elsewhere. There's a number of programming models out there that we need to explore. This is not just an Exascale problem. Even, I would argue that commodity clusters in 2018 or so are going to have things like heterogeneity and deep memory hierarchies and all that. We got to collaborate, and
I gave a somewhat pessimistic view of the Exascale initiative at the beginning, but I do want to point out that we are making significant progress despite the lack of a huge new funding stream. There's CoDesign centers, there's things like XStack, which I know you guys are involved in, and there's this fast forward RFP. So here's my final slide. This is the slide I added just for you guys. I think where we're interested in exploring Charm is for all the things that Charm is best at, and that's this idea of a dynamic runtime system. I'll point out, clearly Charm has staying power. If you had told me when I graduated in 1994 I'd be back here, talking to a group this size about Charm++. Well, that's part of it. So, until now, at least in the really big major apps, MPI has carried the day, and we know that's no longer. So we're struggling to figure out what to do next. I think looking at Charm or AMPI and our algorithms, that's something that we want to do, and I think we'll work with you guys to develop some proxy apps that would help demonstrate the advantages of Charm and vice versa. So this is CoDesign, right? It's just between the applications and the software developers this time. Has Charm's time to shine arrived? I've always said I think it was probably ahead of its time in a lot of ways, because MPI everywhere worked really good for a long time, and there wasn't the forcing function, if you were, for people to necessarily have to begin to reach outside the box. Well, that's changing. I hope I made that clear, and so that obstinacy pays off in the end, right? This is you guys, there's other things out there, like you mentioned some of the competitors, HPX and Swarm, which is the ETI, that looks very Charm-like. But Charm is the only thing robust enough that I see on the horizon today to begin to explore some of this. So this is where we want to be, is getting some exploration, understanding, okay, can we rethink how we do our algorithms to take advantage of these programming models. So maybe next year me or somebody else will come back to this workshop and give a talk on how much success we've had with Charm++ on some proxy apps, or maybe even in some production applications. So, all right, that's all I had. Thank you for indulging me.
Thank you, Rob.
Yeah. So on one of your slides, you had pointed out that there's stuff coming, but none of the new programming models are really ready yet. How do you know when they are ready?
That's a good question. I would say for us, they have to be able to run literally everywhere and quickly on the serial #1 machines. BlueGene Q, we're expected to use that on day one, and we're getting the first one. If Charm++ is ready to go on day one, and you can say the same about Titan and all the other platforms that are even coming up. That's sort of the biggest barrier. It cannot be, a showstopper for us being able to port to these new and very advanced platforms. I think other things like, documentation and, robustness, and the last thing you want to do is, rely on a project that doesn't look like it has staying power, that sort of thing. So I would say of the landscape, I think Charm++ is, the closest of a lot of these to meeting that bar. That, again, that's part of the reason I'm here, is to understand, is it there? I don't know. So.
Maybe there's a related point when you're talking about, reorienting the codes to a new programming paradigm. And you said we cannot start rewriting those codes today because we don't know. And that we don't know partly what you said just now, but also partly what the machines will look like.
Yeah, I'd like to think that, I don't want my programming language to have to reflect the underlying machine. I'd like the abstractions that are rich enough in that programming model or programming language so that I don't have to worry about that. But that's hard. That's asking a lot. I don't know what features Charm has in it, for example, to handle computation at various levels of memory hierarchy. But I want to be able to say, oh, this class or this object, I want to run that out on Flash, or I want to run that out on storage. What features does it have for heterogeneity? I want all this stuff to, that's why Chapel was attractive. They don't have this now, but they've got these ideas in their roadmap, and they seem to have found that, I would say sort of nice middle ground of abstractions to deal with a lot of these things, but it ain't there yet. It's nowhere near as ready as Charm++ is today. Yes?
So at what point will the success of Charm++ allow us to influence the system software, the hardware, to be part of the CoDesign process?
Oh, that's a good question. I don't know if I have an answer to that. I would hope soon. I think everybody's recognizing that this, dynamic, and the idea of dynamic runtime systems is more important, moving forward. So, I don't know. You could probably answer that better than I can, to be quite honest.
At the abstract level, like that probably now, right? But in some other sense, maybe not at all. Because I've heard Phil say, well, architectures are kind of like, for Exascale, the machine design, the process design, will be too late to modify that in the memory standard. But, the rest of the system stack, and even some hard parts of the hardware, I think there is
So to answer that, I would say that the Charm++ heavily influenced both the BlueGene-P and the BlueGene-Q system software, and that indirectly the hardware. If you look at, part of that is to do with the fact that Samir Kumar graduated from this group and now is responsible for designing the middleware. But if you look at things like interrupt-driven communication on VGL, VGP, the wake-up unit on VGP, these things have uses in other places, but they're certainly of direct relevance to any active message runtime or to RDMA-based runtimes. There's a whole bunch of hardware that's unfortunately not exploited by MPI in the BlueGene, and that hardware is exploited by Charm++ and other ones.
Yeah, good point. I didn't show a slide on, but we're doing a hard modeling project right now at Livermore, and they're basically doing the model in the entire beating heart, through a few repetitions or whatever. And, the overheads of MPI, was killing them, and they had to go, sort of 1 or 2 levels down into the underlying, system software to get the performance they needed. And, ideas like that, and like Charm++, I think are going to influence, the higher level abstractions. They have to, right? Because, I'm way over.
Let me ask a quick question.
Yeah. In the Proxy app, how do you make sure that you are replacing this clinical block? How do you make sure that the app is still representative of the full application? Because the timings are different.
Yeah. And are you talking about the skeleton apps or just in general, the Proxy?
In general, the Proxy.
Yeah. Well, I said before, that's an area of open research for us to make sure that, and, if you have ideas on, what are the right metrics for us to collect, I think that's something we've got to address quickly. I will say Sandia has a relatively significant effort in this year. They what's called an L2 milestone in program speak to basically explore that exact question: is how representative are their proxy apps of their real engineering code? And so we'll take some inspiration from that, but we're already starting to look at that by throwing all the tools we have at it. And right now, we're just really in the process of trying to understand the gap analysis of what should our set of proxy apps be. Next step is, are these representative?
I think there's an SCP provider here with there on the proxy app.
They probably was, yeah.
That's
And we're going to do a tutorial this year, one-day tutorial on proxy apps, Sandy and Livermore, and maybe another lab, where we'll get to dive in and do some hands-on stuff with at least LULESH and Mulard, and then the main TiVo apps from Sandia. So check that out if you're interested.